This is amazing result, actually, because when we have plate that is oscillating like this, okay, can we use this model to this kind of physical situation? No, because in this case, when I oscillate, the fluid particle over here oscillate, then this oscillation will affect the oscillation over here and over here. So, in this case, we cannot say that the wall is locally reacting. Okay? It's not locally reacting. But interestingly, later on, we will find that if we find the fluid loading impedance of this kind of plate, then we can directly use this result by just employing fluid loading impedance of plate. What if I have a wall like this? Okay? Then, if we know the fluid loading impedance of this kind of wall, then we can also use the formula that we just got. I mean, the only difference is the partition impedance. Partition impedance. So generally we can say the transmission loss or transmission coefficient can be written as like this. So this is a very general result. Now let's look at the detailed physical implication of the formula we have over here. Okay, what about magnitude square of transmission loss? That will be what? Can you, what is the magnitude square? 4z0 square and 4z0 square? No?
2z0 plus.
Okay. RD plus 2z0 square. Okay. Plus omega m s over omega minus square. So everybody agree? Okay. Let's use a democratic policy now. Okay, that is that behaves according to the natural frequency of a partition. Because what if omega m minus s over omega is the same? meaning that omega square is S over M, and that we know that that is the natural frequency of partition, undamped natural frequency of partition, more strictly speaking, right? So if omega is the same as omega 0, then the transmission coefficient magnitude square, that is equal to what? 4z0 square rd plus 2z0 square. In other words, in this region, this is totally controlled by the linear damping. Right? We can say that. Damping controlled region. Okay, next, what if omega is very, very high than omega 0? This motivated us to write down this transmission magnitude scale expression with respect to omega 0, right? So let's divide this form by omega 0. Right? That means omega 0 is a sort of flag frequency that characterizes the global behavior of this transmission loss coefficient. Right? So if you do that, when omega is greater than omega 0, meaning the natural frequency, therefore I will divide this by m, okay, then I will have S over m over here, okay, S over m over here. So what I have is 1 or omega minus S over m, and I have omega, and this is omega 0 square. So if I divide both sides, so I have to divide 4z0 here by m, right? And also I have to divide rd2z0 divided by m, right?